Welcome back. In the second half of this lecture, we're going to talk about the indefinite integrals for the other four trig functions. We already know an indefinite integral for sine and cosine, but we didn't have one for tangent or cotangent or secant or cosecant, and soon we will. And we're also going to look at some definite integral problems and a little differential equation at the end as well. So to start off with our trig indefinite integrals, the one thing we're going to find for all four of these, for the other four trig functions, is that they're all going to involve a logarithm. For tangent and cotangent, they're both fairly easy to generate yourself because tangent, you know that you could rewrite that as sine divided by cosine. And once you've done that, hopefully it's pretty obvious the substitution that I'm about to do. I noticed that the derivative of cosine is negative sine, which is almost what I've got in the numerator. So if I were to let u be cosine, then du would be negative sine dx. Or in other words, negative du is sine x dx. So doing my substitution, I'll have that negative taken outside. Sine x dx, I'm replacing that with negative du, the negative, and there's the du. And u is replacing cosine of x. So instead of a cosine in the denominator, I've got a u in the denominator. And then now we're almost finished. We get negative natural log of absolute of u plus c. And then we back substitute and say negative natural log of cosine of x plus c. Just one little side note that I wanted to mention about this. This is another place where you will look at some online programming system and it will come up with a different answer maybe than I'm giving you here. And it's not going to be another case of, oh no, he's made a mistake in the notes. It's a property of natural logs that we can rewrite a lot of these integrals in all sorts of different ways. So in particular, if you're thinking about this one, I mean, cosine, natural log of cosine with a negative in front, that negative could be brought in as a power. In other words, we're talking about cosine to the power of -1 or reciprocal of cosine, which is secant. So I could actually rephrase this as natural log of absolute of secant plus c. And if you did that, if you took the derivative of natural log of secant, you would get 1 over secant times the derivative of secant tangent. And yep, you would indeed get tangent back. So there's not just one correct answer for what is the indefinite integral for tangent. Negative natural log of cosine is one of them, and so is natural log of secant. That's another one of them. And that's going to be the case for all four of these. They have various different ways that they can be rewritten. So if you're comparing the answers that I'm getting here to ones that you might find in a different book even, you might find different indefinite integrals given, and it's just for that reason, because we've got log properties that can allow us to rewrite things. Okay, cotangent, we're going to do much the same, except in this case it would be cosine over sine. And we're going to have an easier time here even because when we are letting u be sine, then du is exactly what we have in the numerator already, cos x dx, which means that our integral is going to change into just 1 over u du. And so we'll have natural log of absolute value of u plus c, or in other words, we'll have natural log of sine of x. Okay, secant and cosecant, these ones are a little trickier and less obvious. Secant, in a way, I mean, we're sort of in luck because we did look at it earlier, except when we looked at it earlier, we were looking at it as a derivative. We had a function natural log of secant plus tangent absoluted, and we found the derivative of that was just secant. So we actually kind of already know the answer to this. The clever trick that we need to be able to go from an integral of secant to something that we can actually integrate is multiplying top and bottom by secant plus tangent. So that's going to be the clever trick that I'm going to do here. I have my integral of secant, and I'm going to rewrite it as integral of secant times secant plus tangent. And the reason we're doing this is because if we were to let u be the denominator, if u was secant plus tangent, then for du, you would have secant tangent and secant squared dx. And that's exactly what we have in the numerator. I have a secant times secant. I've got a secant squared plus a secant times tangent. So the entire numerator is going to be replaced with du, and the entire denominator is just u. So we wind up with just 1 over u du. So we're going to get natural log of u, or in other words, natural log of secant plus tangent plus our constant c. So if we remembered this one, then that's actually going to give us a good hint as to what to do for cosecant. So for secant, we multiplied top and bottom by secant plus tangent. No shock here, I'm going to multiply top and bottom of cosecant by cosecant plus cotangent. And the reason I'm doing that, of course, is because if I were to think about letting u replace that denominator, then I know as far as differentials go, du would be negative cosecant cotangent and minus cosecant squared dx, which is exactly the negative of what I've got in the numerator. I have a positive cosecant squared and a positive cosecant cotangent, so that is just negative du is what's going to replace my numerator. I could say that I know that negative du is cosecant cotangent plus cosecant squared. I'm going to have to correct my writing. I said cosecant squared x, and I wrote cosecant of x squared. Sorry about that. There we go. So we have negative du is going to replace my entire numerator, and u is going to be my entire denominator. And so there we go. We can say that we have minus integral 1 over u du. And we know that that's going to be negative natural log of absolute value of u, or negative natural log of cosecant plus cotangent, plus our constant c. Okay, let's do some definite integral time. I have a definite integral from 1 to 3 of this function. For sure, the discontinuity for this function is at -1, so I don't have to worry about does my integral exist or not. Yes, it certainly does. This function, x minus 1 over x plus 1, is nice and continuous. And if we're thinking about what we did previously, when we had a rational function, we turned it into polynomial plus rational function with a little bit of division. And I could do the same thing here. If I took x plus 1 and divided it into x minus 1, x goes into x once, and when we multiply and then subtract, I get a remainder of -2. So that means my definite integral could be rewritten as quotient plus remainder over my divisor. So in other words, what I had here really could be written as 1 minus 2 over x plus 1. And then we're pretty much good to go. To evaluate this, I just need to find an antiderivative, and I know for 1 it's x, and for 1 over x plus 1 it would be natural log of x plus 1. Here I'm going to be lazy, and I'm not going to use my absolute values, and the reason I know I don't need them is I'll be putting in numbers between 1 and 3, and x plus 1 is certainly going to be positive in that little interval, so I don't have to worry about my absolute value. I just need to go now and evaluate between 1 and 3. So when we evaluate at 3, we'll have 3 minus 2 times natural log of 3 plus 1, and then we'll have minus 1 minus 2 times natural log of 2 plus 1. I can do a little bit of cleaning things up here just to make things nice. I have a 3 minus 1, which is 2. I have a natural log of 16. I have a plus natural log of 2 squared, which is 4. And I could, of course, combine these two logs together and say that this is natural log of 4/16 or natural log of a quarter. And in fact, if I wanted to go and do one last little bit, just to make it, this is where I would end it personally. Natural log of a quarter is natural log of 1 minus natural log of 4, and natural log of 1 is 0, so I think that's a nice looking answer for me personally. 2 minus natural log of 4. That's where I'll leave my answer. If you stopped up here, I mean, that's totally fine, or even here is fine as well. I'm not bothering to do any approximate decimal answers. I just want an exact value, and so really any of these would have been acceptable for me. Okay, let's take a look at one more definite integral problem. We have a function, and we want to find its average value. So this is one, again, where if we're looking at it, even though it's not asking us to find a definite integral, I know a definite integral is part of it, because if I'm looking for an average value of a function over an interval, then that would be the average value would be found by taking my definite integral from 0 to 1 of f of x, and then in the front dividing by the length of that interval, 1 minus 0. So my interval, conveniently enough, only has a length of 1, so I'm only averaging out by dividing by 1. So really I just have a definite integral from 0 to 1, and it's of secant of pi x over 3, or pi over 3 times x. I probably would want to do a little bit of a substitution here just to help make things easier for me. I mean, I know my antiderivative for secant, but I know I probably would stumble on the pi over 3 part of things. So if I just quickly say that I'm going to replace u with pi over 3x, then I know du is pi over 3 dx. In other words, 3 over pi du is what's going to replace my dx. So as far as the integral part goes, instead of secant of pi over 3x, I would have secant of u, and dx is being replaced by 3 over pi du. Remember, as I said before, when we were evaluating with substitution a definite integral, our choice is either do an indefinite integral on the side, then do your back substitution and evaluate afterwards, or if you wanted to, you could, after you've done your substitution, keep it as a definite integral, just making sure that you change your limits of integration. And that's what I'm going to do here on the side, because it's not too hard to do. We can say for sure if x is 0, then for sure what u would be pi over 3 times 0, which is 0. So our lower limit of integration is still going to be 0. And then for the upper limit of integration, x is 1. Well, what happens when x is 1? U would be pi over 3 times 1, or in other words, u is pi over 3. So that's my plan here. I'm going to actually keep things in terms of u's. I'm not going to bother doing any back substitution, because I know that after I find the antiderivative for secant of u, I can just evaluate at pi over 3 and at 0, and then I'll be finished. So that's what I'll do. I know for secant of u, the antiderivative for that, or an antiderivative for that, is natural log of absolute value of secant plus tangent. And we're going to evaluate that between 0 and pi over 3. So when we evaluate at pi over 3, that's not too bad for us to do, because I will have natural log of secant of pi over 3, which is which is positive 2 rather, tangent of pi over 3, which is root 3. So there we go. We've evaluated at pi over 3, and then now when we evaluate at 0, we would have natural log of secant of 0, which is 1, plus tangent of 0, which is 0. And then as my last little bit here, I mean, this last little natural log is really natural log of 1, which is 0. So all I'm left with is this first natural log times 3 over pi. So looks like 3 over pi natural log of 2 plus square root of 3. And there we go. That should be the average value of that function over that interval. Okay, well, one last little problem to solve, and it's a differential equations problem. I have a second derivative here, and I want to find out what is my function f of x. So I'm going to start off by saying, well, I know that if I wanted to find f prime of x, I could find that by looking at finding an antiderivative of f double prime of x. And that one's not bad. It's, what, negative 4 over x minus 1 squared minus 2. As far as things go, I mean, you could certainly do a substitution if you need to. So if you weren't feeling comfortable, you could say let u be x minus 1, and so du is being replaced with dx. So really it's minus 4 over u squared, or minus 4u to the negative 2 minus 2 du. And easy enough for us to find an antiderivative for that because we're just using power rule. We're going to add 1 to the power and divide by the power. So we'll have minus 4u to the minus 1 divided by minus 1. And then for the second term, it would be minus 2u. And then plus a constant c. And then the next thing that I would want to do, of course, is to clean things up. So the 4 and the 1, the negatives will cancel each other out. I'll have 4 over u. U is the same thing as x minus 1. Minus 2 times x minus 1 plus our constant c. And now I'm going to use and of course this was f prime, so all of these are what f prime is. So I've now found my first derivative, and I'm going to use one of my initial values, and the initial value that I'm using is that f prime of 0 is equal to 2. So I know what x value I'm putting in, it's 2, and I know what y value I'm hoping to get, it's 0. So now all I need to do is figure out what is the constant c that will make that happen. So let's put in our 0 for our y value and 2 for x. So this is using f prime of 2 is equal to 0. And we get 0 is equal to 4 over 2 minus 1, that's 4 over 1. And we have minus 2 times 1, which is 2. And so finally, after I clean things up, I'll find that c is equal to negative 2. And so now we can say, therefore, f prime is 4 over x minus 1 minus 2 times x minus 1 minus 2. We could clean this up a little bit further, of course, right? So if I were to expand things, and I do intend to expand things a little bit further, I can say that you'll have minus 2x. You would have a plus 2 and a minus 2. So the plus 2 and the minus 2 would be gone, meaning that really this is the simplified version of what f prime is. So we now know what f prime is, and now we just need to do one more step to figure out what f is. So f prime, we said, was 4 over x minus 1 minus 2x. And if we wanted to find out what f is, f of x would be an antiderivative of that. And we also need to have handy our initial condition, because we'll need that for later on. The other initial condition we'll need to remember is that f of 2 is 3. So I'm just going to make a little note here for myself for later on that f of 2 is 3. Okay, so we start off with integrating 4 over x minus 1 1 over x minus 1, an easy antiderivative for that is natural log of x minus 1. For 2x, we've seen that one so many times now. Its antiderivative is x squared, and we've got a constant c to throw in the mix. One thing I should probably do, and just to be proper about it, I really should use c1 and c2. And that's because, of course, we have two different constants and they may or may not be the same. So my second constant of integration there, I'll call you C2. And now we're going to use our second little initial condition, which is that when x is 2, y is 3. So using f of 2 is equal to 3 would give us 3 equals 4 natural log of 2 minus 1, which is 1, minus 2 squared, plus mystery constant C2. Natural log of 1 is 0, so this whole term is gone. I really have 3 equals 0 minus 4 plus C2, which means C2 is 7. So now I can say with confidence that my function is 4 natural log of absolute value of x minus 1 minus x squared plus 7. And again, same thing I wanted to mention that I've said before several times about differential equations. We can confirm our answer. Now that I have my function f of x, if I were to take the derivative of this function twice, I should get this second derivative. So I can confirm my answer very easily. I can also confirm that it satisfies the initial conditions. I mean, I can certainly check right here that if I put in 2 for x, that I should certainly get 3 as my y value. The other thing I can check is that after I differentiate this function, and if I did, I would indeed get f prime that I've got up top, I can confirm that this also satisfies the other initial condition that we had. The one last thing that I'm going to do here, and this is something that we didn't really pay attention to at the start of the problem, but we'll notice it here. You might have noticed it when I flashed back, that here specifically we're talking about only looking to solve things when x is greater than 1. And if that were the case, if we knew x had to be bigger than 1, then x minus 1 would be guaranteed to be positive, which means that actually when we write things out at the end of it all, we don't really even need the absolute values anymore because we know that x is greater than 1. So actually now I can say, here's my function without absolute values, and that will be my function for x greater than 1, because we were only looking to solve our differential equation for values of x that were greater than 1.